All right, we are set now. Let us begin. So, uh, in the previous class, we were discussing these problems. And by the way, yesterday I uploaded the tutorial sheet number 10. Okay. However, I am not directly going to start solving problems from that. Rather, I will continue to solve these uh, relatively simpler problems, because it is in my experience that once we do these things, then more involved problems the students can attempt on their own. So actually this energy methods chapter was there previously also. Okay, so uh, I know what experiences the students have. So I'll continue with these simpler examples, but very important. So you please note. So the next thing that we are going to consider is again a cantilever beam, but the question is slightly different. So we have this beam. Let's say this is A, this is B. The question is, what is the, so if a moment is applied at this end, and let the magnitude of this moment be m naught, then question is, what is the slope at this B? Okay, so in terms of the spirit in which we want to solve this problem, there is not much different from what we were doing earlier, except that if you just look at the previous problems, we were trying to find out the deflection, and that we did by differentiating the total strain energy of the structure with respect to the force at the point in which we want the deflection. So for example, here we wanted the deflection in the vertically downward direction at this point, and we had the force also at this point, so we could do this. So now, since the question is of slope and this moment is also given, for the slope, what we just have to do, if you just go back to the statement of Castigliano's theorem, you see this one. Okay, all this while we were doing this thing, now we are going to use this, that the slope is equal to del u del m. Okay, so as usual, we take a cut section, we draw the free body diagram of this right end, this is our general M, and there will be a shear force also. I'm showing that for the sake of completeness, we don't require that for our solution steps. And this M is going to be equal to m naught. This is the moment balance equation. It's pretty straightforward. Now for the theta, the general equation that we have is del u del theta equal to del u del m. Okay, so let's simplify this a little bit. The u can be written as m square by twice ei. This integration of m square by twice ei dx, integration limits being 0 to L, where please note that I am taking the x starting from here. Okay, so x equal to 0 is at B, x equal to L is at A. Now as before, I can take this differentiation within the integration sign. I don't have to worry about the Leibniz rule, because both these limits of integration are constants. So this becomes m by ei. So actually it is twice m by twice ei, that 2 cancels, and then I have del m by del m naught. Okay, it is del m by del m naught for this particular problem. Okay, so please note that this is actually del by del m naught. Okay, now this is just a matter of substitution. We substitute this m naught here. Del m by del m naught, what is it? Tell me. What is del m by del m naught?
1.
1. So the answer basically comes out as m naught L by EI. All right. Now you may be wondering that suppose instead of this m naught we were given a force P here only. Okay, so what I'm asking is this: suppose we had the same cantilever beam like this, and instead of the moment this force was given, so our usual problem. Now in this case also this beam is going to deflect. As a result, there is going to be some slope at this end. How are you going to find out the slope at this end? Any ideas? Because see, here we were able to do the del m naught. This m naught is like the counterpart of the theta in terms of the work done. Okay, in terms of the work done, if you are dealing with deflections, then the counterpart of it in terms of the the work done, or the conjugate of it, will be the force. If you are talking about angle, then the conjugate of it will be the moment, because if you multiply deflection with force you get Newton meter, that is the work done. Similarly, if you multiply the slope, which is in radians, with the moment, and the moment itself as the unit of Newton meter, so moment times slope is equal to work done. So in that terms I'm saying that this is okay. But suppose here you are given the force and you are asked the slope at this end, then what will you do? Because no moment is applied here. What will you differentiate? So I mean, there is no problem with finding out the total strain energy of this cantilever beam, because you can take a cut section here corresponding to this force, you can find out the moment, and then just by using this m square by twice ci integration 0 to L dx, you can find out the total strain energy. But what will you differentiate that with? That is my question.
Yeah.
Sorry?
P
P into L? No. That will be wrong. That will be wrong. Because see, what we are applying is actually P. Okay, the moment, the internal moment which is being generated, that is Px. The moment that is applied, that is not Px. There is a very subtle distinction between the two. Okay, here this P is the external force. Here the shear force that is generated, that turns out to be V equal to P from a force balance, but V is not the externally applied force. So it will be incorrect to say that you can just do del U del V for deflection. Okay. So in the spirit of what you just said, suppose if I want to ask in a very similar fashion that this situation is given and I am interested in finding out the deflection at this point, at the midpoint or any distance within this beam, then what will you do? Same issue. Okay, here I was asking about the slope there, but there was no moment. Now structure is the same, loading is the same, I am asking about the deflection at some other point.
I don't know, virtual force theorem, put a virtual force, then find the expression for the total strain.
Right. So before discussing the Castigliano's theorem, we were discussing the principle of virtual work, and there we were dealing with this kind of situation only. Okay, the question there was that if you have a general structure like this under some general kind of loading, then at any given point where maybe there is no applied force, can we find out the deflection? The answer was yes, and that was by the application of a virtual force at that location. So just to refresh your memory, let me jump back to those previous slides. You can see for yourself what we were discussing earlier. You see these things. We had a general body like this. We had various forces and supports, and our question was to determine the deflection at this point where, mind you, there is no force here. So we applied some virtual force, and by following these steps, we were able, we had a recipe for determining the deflection. We can do that. That is the principle of virtual work. But my question now is that within the context of the application of the Castigliano's theorem, is it perhaps possible to do such a thing? Or is it that Castigliano's theorem is just limited to these kinds of problems? Okay, so the things that you are suggesting that has the kernel of the idea which is necessary for us to go ahead with these kinds of problems. The answer, of course, is yes. Using Castigliano's theorem, it is very much possible to solve these kinds of problems where we are interested in determining the deflections at those points where no force directly is applied, as well as we can determine slopes at those points where no moment is directly applied. Okay, and that is using by some kind of dummy or fictitious force. Alright, so we will take up such an example right away. Okay, so slightly different problem. I want to take different kinds of structures because I'm repeatedly taking this cantilever problem with point force. Instead of that, let me just take slightly different kind of problem. The steps will be somewhat different, so it'll clarify the general ideas of solving problems even more in your brain. So not very different. You have seen this situation before. It's a cantilever beam under uniformly distributed load. But the question that we are going to ask ourselves is that what is the deflection at this point? Okay, because you see, this is a uniformly distributed load, and the recipe which Castigliano's theorem tells us is that you have to do a del u del p for the deflection. But where is the p here? There is no direct p here. There is a distributed load here, fine, but there is no direct point force here. What can we do? So when we don't have a point force, we introduce a point force artificially. We do whatever we want to do associated with that point force, and then ultimately in the answer, we set the magnitude of that point force to be equal to 0. Okay, so said in words like this, it seems like a very complicated thing, but actually it's really straightforward. And if I just show you, you will see how simple it is. So what I'm going to do is, I will just apply this this force, this fictitious force. I hope you can see this purple color on green. It's not a very good combination. Can you see this purple color on green?
Yes, sir.
Okay. So this is the fictitious force. Okay. So let's say this is W, this distributed load, and this fictitious force, let's call this, we call this P. Okay. And our idea is that we will solve this this artificial problem with the P introduced, and then at the very end, we will put this P equal to 0, or somewhere appropriate, we'll put the P equal to 0. Okay, so now that we have this problem in our hand, what are we going to do? Our first job is to determine the moment at a general cut section. So usual process. We take a cut section, we consider the free body diagram of this left part now. this one, and this is M, this is V as usual. And if we do the moment balance, what are we going to get? This M is in the anti-clockwise sense. The contribution from P when we take the moment about an axis which passes through this right end will be, so this is X, okay. So it will be plus Px or minus Px?
So plus Px.
Plus Px. And then the contribution from this distributed load?
Wx square by 2. Positive.
Yeah, Wx square by 2. So our M is going to be equal to minus Px minus Wx square by 2. In response to this M, or associated with this M, there will be a strain energy U. But now you see, we already have the steps that we require to find out the delta. When I write this delta, I have to remind myself that I wish to find this delta associated with this artificial situation, and to make this artificial situation switch back to the actual situation, what I'll have to do is I'll finally have to use the condition that P is equal to 0. So with this understanding, I proceed. So just like before, I'm going to write the expression for the delta in this form: M by EI del M del P. So what is this thing? Let me just switch back to one of the earlier slides where I discussed this for the first time. This is delta equal to del U del P, and then I took the differentiation within this integration. It came out as M by EI del M del P integration 0 to L dx. So this is kind of the general thing that we are going to use every time. So that is exactly what I have written here. But now please note that this entire thing has to be evaluated with the understanding that P must be equal to 0. So let us substitute the expressions now. For M, I am going to put minus Px minus Wx square by 2. Del M del P. Del M del P is what? Tell me.
So minus X.
Del M del P is minus X. You see, this is a crucial step here. You also note that in going from here to here, I have not first substituted P equal to 0. That would have been wrong. Because, let me just give you an analogy with what you already know from your high school mathematics. High school means plus 2 mathematics. So suppose you have a function like y is equal to x square, and you are asked to determine the value of the first derivative of this function at x equal to 0. So you don't do like this, that you put x equal to 0 and then you do dy dx. Then that value will be 0 artificially. Okay, rather what you do is you first do dy dx. I mean, x equal to 0 is not a very good example because the answer comes out to be correct. So dy dx equal to twice x, and then you substitute x equal to 0. For x equal to 0, answer is correct even if you put first x equal to 0. So perhaps x equal to 2 or x equal to 3, something like that. Okay, because if you first put x equal to 2 here, it becomes a constant value, and then you do dy dx, it will never come out anything other than 0. Okay, similar situation is here. First you do the partial derivative with respect to p, you get this expression, and then you set p equal to 0. Okay, now if you set p equal to 0, there is no problem. I mean, in fact, the algebra will become easier because this p will go away. So you are left with, sorry, I made one mistake. I didn't write all these integration things. So we still have the integration. and over all of this there is this P equal to 0. Now no worries that this P equal to 0 is over this entire thing. We can peacefully set this P equal to 0 even within this integration. So this is minus Wx square by 2 multiplied with this minus x divided by EI. So do this calculation and tell me what is the answer. EI is constant, okay? What is the answer? Tell me.
Wn to the power 4 upon 8 EI.
Good. Wl to the power 4 by 8 EI. Please note that each time we are doing these integrations, we are considering this EI, Young's modulus times the second moment of area, to be a constant quantity. However, there may be some general problems where the beam is not prismatic. Not prismatic means that the cross section of the beam may be varying along the length of the beam. Along the span of the beam, the cross sectional area may be varying. In which case, the second moment of area, that is the I, that is also going to change. In fact, that I will then be a function of x. For instance, a slight generalization of this problem could be like this, that you have a beam which is shaped like this. And I am not just cooking it up, this kind of a situation, I am not just cooking this up for the sake of making the algebra more involved. Rather, this kind of a structure of the beam is actually very common. For instance, you can see it in some of the homes and office buildings also. Where can you see this? It's very common to see this kind of a beam being used as the support for the outer units of split ACs. Okay, so I mean, here in IIT Kharagpur it becomes very hot and humid, so we have to use ACs in our offices. And some of the modern AC installations, air conditioning installations, they are mostly used as like this split units. Okay, they are not the window AC kinds. And the outer units of this, most of the companies, they use these kinds of non-prismatic beams as the supports on which the outer unit is resting. Okay, so you observe it. If you have a AC at home or maybe some office, you can see, you'll be able to see this. Okay, so in this case the I will be varying along the length. Okay, in which case you will not allowed to take this I out of this integration. Okay, you have to know how the I is varying along x, and that thing will become part of the algebra here. Okay, all right. So this way of doing the problem of finding deflections at those points where no direct force is available is referred to as the dummy force method or the fictitious force method. And please note that this is very much part or within the scope of the Castigliano's theorem application. Okay, do you have any question regarding this part or up to this point? Because each time I am showing you an extra example like this, it is opening up a huge lot of possibilities in framing questions. Okay, so unless you are absolutely sure about what you are seeing being demonstrated here through these examples, it may be difficult for you to apply these things in more involved examples. That is why I am asking. Do you have any questions up to this point?
Sir, the differential equation method that we studied,
yes.
Doesn't that have any, advantage over this? We can take out deflections from this now. So what does that, how does that help now? We can take force in this method, deflections in this method, take out deflections.
Yes. So there is a choice now in your hand, that if you are asked to, if you're just shown a structure and somebody is asking you that find out the deflection at this and this point, you just apply whatever is comfortable to you. Nobody is going to force you that you solve it by the deflection method or you solve it by the energy method. But I can tell you one thing, that once you learn the energy methods, it is very hard for you not to use the energy method. Okay, it is very, very tempting to use energy methods all the time. In fact, like there was a suggestion yesterday that even if you have to determine the deflection as a function of x, it is still possible to use the energy methods to determine that. Okay, now your question was the other way around actually, that what advantage does the deflection method have over this? Was it not?
Differential equation method.
Differential equation method, right? So the differential equation method, I don't know. I am very fond of solving differential equations. I like that method also. I don't know. I have to think about it. I have never thought it like that. I have always thought about what great advantages the energy methods have over the deflection method, but I have never actually thought the other way around. I'll try to think and come up with something if I can. Okay.
Sir, I think if we go by differential equation method, we don't need to solve the problem again and again for different points for the same kind of load.
That is not exactly, a valid thing, because this delta we can find out as a function of x even using the energy methods. That is possible. Okay, so you said that. Now let me show you how you can do this. I was not planning on showing this, but let me just discuss this quickly. So suppose we have this our favorite example of a problem, the cantilever beam, okay, under point load. So this is our thing. Okay, and the question is that, is it perhaps possible to use energy methods to find the deflection at any point generically? Okay, just like in the deflection chapter, we were finding the deflection as a function of x. Can we perhaps use the energy methods to find out the deflection at any point generically as a function of x? Can we do that? Of course we can do that. So you see, all that I have to do is apply a fictitious force at some distance. Okay, so let's say at some distance I apply this fictitious force q with the intention that ultimately I will set this q equal to 0.
Yes sir, got it.
So then you see what is going to happen is that this q is applied at some generic distance, let's say x0. Okay, now in response to this you have to find out the moment. It is now like a problem involving two forces. So there are two parts now. From 0 to x0 there is one part, and from x0 to xl there is another part. There are two segments to this beam. So you first have to take a cut section between the forces P and Q, and then you have to take another cut section between this point and the end. And then after you have done the overall problem, you will get your answer in terms of the x0. That x0 itself can vary from 0 to L, and that is how you get the deflection as a function of x. Rather, you find it as an x0, but you understand what that is. Okay, so I suggest that for this simple problem you try this. Okay, the same situation is with the previous problem also. Here also it's the same situation. Suppose, we have found out this WL to the power 4 by 8 EI as the deflection at this end. But suppose instead I had asked the general question that what is the deflection at any point which is at a distance x naught from this end. Then you would have applied this force P. Instead of at this end, you would have applied it at a distance x naught from the left end. And then for this complete problem where W is applied together with this fictitious force P, you would find out the strain energy. Now you would first find out the moment, and then you would find out the strain energy, do all these differentiations, set this P equal to 0, and then ultimately the answer that you will obtain for the delta will involve the x naught. And you will understand that this x naught itself can be varied from 0 to L. And that is how you say that, yes, I have found out the deflection as a function of x. I hope this is clear.
Yes, sir.
Yeah. Okay. Another kind of situation is that, I mean, it's probably simpler than, so this was actually what I was going to discuss. So suppose you have this. I am not again going to solve this, I'll just show it to you. So suppose we have this, again, this cantilever beam. And I apply the force here. Let's say this distance is some A. All right, and the question is that what is the slope at this end?
So that will be same as the slope at distance A.
That will be same as the slope at the distance, I mean, not A, yeah, I mean, this distance, L minus A from the left end, right?
Yes.
Yeah, but I mean, how are you formally going to determine the slope, the value of the slope? That is my question.
So if we take a section in the extent, I mean at the tip point of the cantilever beam, so M would be 0 there.
No, but you are asked the slope, na?
Yes, sir. So we will divide the interval to 0 to L minus A and L minus A to A.
No, suppose I ask you that you directly find out the slope at that end, at this end, directly. So the reason I'm forcing you to think like this is that you please try to think in terms of what we just discussed in the previous page, this one. In this page, whatever we discussed, you see, I was interested in determining the deflection at a point where I did not have a force. So try to think in those terms. I am now asked to determine the slope at a point where I do not have a moment. So what do I do?
So we introduce a dummy force.
Not dummy force, not dummy force. So whenever you are asked a slope, you introduce a moment. Okay. So for this, let me just tell you, let me just write this. Introduce a dummy or fictitious moment. Let's say this is A, this is B. We are asked to find out the slope at B. So a dummy or fictitious moment at B. So basically the exact same thing as this. Except that now we will consider a moment like this. This is the fictitious moment, okay? And now whatever you do, so the idea is like this, that you write something like this, theta at B. So theta at B will be the value that we'll obtain by setting moment m not equal to 0 after doing these steps. of course, as you correctly pointed out, that this 0 to L integration, it is all right to write this general formula like this, but for the sake of this problem, since there are two segments, one is from this 0 to A and the other is from A to L, we'll have to subdivide this integration into two pieces, 0 to A and then A to L. Okay, so 0 to A, the value of M will be simply M naught, and then from A to L it will be a combination of the contributions from M naught and this P. Okay, so I'm not going to do all these steps. It will be quite repetitive in nature. Rather, let me just try to address different problems. Okay, so we were discussing up to this point deflections and slopes. Okay, and we were also able to determine deflections and slopes at those points where directly their conjugate forces or moments were not available by introducing some kind of a fictitious or dummy force or moment. Now I am going to change the perspective a little bit. Changing the perspective means, I don't know whether you have noticed or not, up to this point, whatever problems I have been considering as demonstration examples for this Castigliano's theorem example, I was considering statically determinate problems. Okay, so let's switch back to the previous slides and just take a quick look. This was our first example that we considered. Okay, this was just theory before this. This was the first example, cantilever beam, point load. This is a statically determinate problem. Okay, so you can find out all the reaction forces and moments. Next, this is a simply supported beam, very much a statically determinate structure. You can find out all the reaction forces and everything just by using the equations of statics which you learned in your first year basic engineering mechanics. Next, this is again a cantilever beam under end moment, and again you can determine the reactions at this end using the equations of statics. So statically determinate case again. This also very much a statically determinate case. This also statically determinate case, statically determinate, everything is statically determinate. Okay, so now we are going to consider statically indeterminate cases. So let's first consider a cantilever beam, and then we'll make it no longer a cantilever beam by introducing a redundant support. So up to this point, whatever I have drawn, this is statically determinate. In fact, let me introduce the loading that I want to investigate. Uniformly distributed loading. Up to this point, statically determinate. But now I am going to introduce a redundant support. Redundant support means an extra support in the sense that even without this support, the structure was very much standing on its own. So this is like an extra thing over and above what is required. Because of the introduction of this extra support, which is a roller support basically, now it has become statically indeterminate, because you cannot, by using the equations of statics, determine all the reaction forces completely. Okay, so this is the situation. But question is what? Question is the most important question you can ask in a statically determinate problem, is that since you do not have a direct method using the equations of statics to determine the reaction forces, what are the reaction forces? Because unless you have complete information regarding all the forces involved in this problem, you cannot really do much. So tell me, given all your experiences with previous discussions of statically indeterminate problems, what am I supposed to do here? Of course, I am asking this in the context of the application of Castigliano's theorem, so try to answer like that.
So we assume a reaction force R at that point where the support is there by removing that support, and after that we use the same method of Castigliano's theorem and find the slope at that point. I mean deflection at that point, but deflection at that point would be 0 because it is a boundary condition.
Very good. That is exactly the method. Okay. I mean, very, very good. Very, very clearly stated. Good. So, what he said is like this. Our interest here is to find out the reaction force at this point. Okay. I mean, we want to find out all the reaction forces, but since we do not have a direct, I mean, this is the problem situation. What we'll consider is that we will remove this support. This support was creating a problem. We'll remove this support. And when we remove this support, we have to replace this removed support through an equivalent reaction force it was applying on this structure, and that is just the vertically upward force. Alright, so we have that vertically upward force. Now, if you just consider this entire problem again, where I have just removed this support, this roller support, then I am left with this reaction force. Let's call this RB. Now, if suppose, imagine for a moment that this was our given problem, that you have this uniformly distributed load, and in addition to that, we also have this force RB at this end. So, we can go ahead and directly apply Castigliano's theorem to determine the deflection at this point. There is absolutely no problem. But that would have been for that other problem, that where this was our given problem. But this is not our given problem. Our original problem is this. So there is a difference between this one and this one. What is the difference? The difference is that we know for a fact when we consider this problem that the deflection at this point B is guaranteed to be 0. Okay, so under this loading, this downward pointing loading, we know that the deflection in the downward direction is going to be 0 for the point B or the end B. So no matter what you do from this extra or additional or artificial problem that you are considering now, the ultimate condition which we must impose on this problem is that the deflection at the end B must be 0. So overall the situation is like this. When we are starting out this problem, although we have written it in terms of the variable like an RB, but the truth of the matter is that RB is not known. Okay, so even if you manage to find out the deflection at this end B, it is not going to be like a value. It is going to be like a variable in terms of this RB. But that is not a problem because you do have now the extra condition to impose that the deflection there will be equal to 0. So previously, everything that you were doing led up to the point where you could actually determine the numerical value of the deflection directly. But here it is like the deflection will be a function of RB, and then the deflection itself has to be set equal to 0 so that you can determine RB from that equation. This is the general idea. So let us follow through here and try to do the steps properly and try to actually determine the value of this RB force. So what am I going to do? First of all, I am going to take a cut section. I am going to consider this right side. Same force RB. Like this. Okay. Moment. shear force. All right. What is the expression of the moment? Tell me quickly. So you consider the x to be directed leftward like this from this end. Now you tell me what is the expression of the moment?
Sir, RB into x minus WX square by 2.
This will be minus RB, no? M is clockwise. Contribution of the RB to a moment calculated about an axis passing through this left end. That is going to be minus RBX.
Sir, I'm saying final M is equal.
Oh, okay. No, just tell me the moment balance equation. So sigma M equal to 0, that one you tell me. M minus RBX, then?
Plus WX square by 2.
WX square by 2, that is equal to 0. So this gives us M is equal to RBX minus WX square by 2. Okay, now I am going to determine the deflection. So deflection will be integration 0 to L M by EI del M by what? Del M del what? Tell me. I am interested in finding out the vertical deflection at the end B. So
it will be RB.
Yes. So the corresponding force means the force in the vertical direction is nothing but RB itself. So let me substitute the expressions now. M is RBX minus WX square by 2 divided by EI del M del RB. This one, what is it? Del M del RB?
So X.
It is simply X. Integration 0 to L. So tell me the value of this thing. So I will do this integration separately. I will take the RB by EI out of this first bit of the integration. Fine. So this is giving me RB. This is x cube by 3. So this is L cube by 3 EI minus this is L to the power 4 by 4. So this is W L to the power 4 by 8 EI. Now what am I supposed to do? I'm supposed to go back to this deflection and note that this deflection is supposed to be 0. So now you see this deflection equation has given me an equation in this unknown force RB, because on the left hand side I have a 0, on the right hand side I have two terms. This is entirely known because this W is actually given to us. Please note that this distributed load is W. So from here we can find out the value of RB. So RB is what? W. So this L cube, L4 here, L remains. EI cancels. This 3 goes up in this numerator, and then we have this thing 8. So this is 3WL by 8. Please note that this W actually has the unit of Newton per meter, because this is a distributed load. This is Newton per meter. So in terms of dimensions also this is correct. W is in Newton per meter, L is in meter, so overall this is Newton. So RB must be a force that is Newton. So this is actually correct. Okay, so this is the thing. So this is the general idea. So when you are faced with an indeterminate problem, you can use energy methods also to determine the unknown reaction forces. Okay, previously we have seen that using in the deflection of beams chapter, we can determine the reaction forces. Here also same idea. Okay, so these are basically general ideas associated with indeterminate structures. So any question up to this point? Because this is a very, very big, the moment I have discussed this kind of a problem, it opens up a huge lot of possibilities for asking questions. I mean, this is in terms of examination, that it opens up a huge lot of possibilities in asking questions. But even in your professional experiences also, it opens up a huge lot of possibilities in the kind of problems that you can actually tackle. And mind you, in the professional life, the most of the problems that you are going to encounter are going to be indeterminate ones, because real engineers, despite all the confidence and all their abilities in mathematics and doing everything, when actually building a structure, they will introduce some kind of redundant supports just as some extra precaution. Okay, so many real engineering structures will be statically indeterminate. So this is a very, very important step to or method to learn. Any questions up to this point? You please think for a minute and tell me, and then I will tell you some very important thing, and then we'll take a short break. Okay, so since no questions are forthcoming, let me just state that the extremely important thing. It is so important that you write this thing on a piece of paper, cut it out and paste it in front of your study table or whatever, wherever you study, or just put it up on your wall or something. Okay, so this is very important. What I'm going to say now. In fact, it is so important, and it's actually a very dangerous thing. So I will actually draw a skull here. This is very, very dangerous. Okay, danger is this: do not ever use this delta equal to 0 trick to find reaction forces in statically determinate structures. Okay, so if your structure is statically determinate, do not ever use this delta equal to 0 trick. Okay, for instance, if you have this kind of a situation, that you have this cantilever beam and you have this force P, and you know for a fact that the deflection at this end is going to be equal to 0, please do not by some trick try to find out the deflection or the reaction force which is just going to be equal to P at this end through that method. Okay, maybe in some weird scenario you may end up with a correct answer, but in general you will end up with the wrong answer. Everything will be wrong. You are basically trying to impose an extra condition on a problem which is otherwise very clearly solvable using just the equations of statics. Okay, so that kind of an extra imposition of a condition leads to problems. Okay, do not ever do this thing. Even though you know there is nothing wrong with understanding that the deflection here is 0, but do not use that to find out forces there, reaction forces there. Okay, so now we take a short break. So let us begin again. We'll continue discussing our simpler examples. So the next one we are going to consider is again a beam, but its shape is in the form of a semicircle. So it's like this. So this is also some sort of a cantilever but not in the sense that we have been discussing till now. And this structure, it is subjected to this point force acting at its top. So this is a very generic kind of thing, it is representative or an example of a very generic kind of situation. We are going to use Castigliano's theorem to try to do this problem, but you please note that we are going to use the same kind of strain energy formula based on that m square by twice EI expression here also, but that is valid only when the radius of curvature of this semicircular beam, or maybe it's like in the form of some arc, the radius of curvature there. So if it is like this, let's say this is the radius of curvature, that R must be much larger than the depth of the beam. Depth means this much, okay, this is the depth. Okay, much, not just larger, of course it is larger here, but it is, let's say it is much larger than this depth. Okay, so what we actually say is that these kinds of beams, they must be considerably thin. Okay, so basically thin beams. So when we have these kinds of circular or semicircular or arc-wise kind of beams which are thin, then it is all right to use directly that m square by twice EI expression here also. Okay, now what is the question here? This is the situation. What is the question? Question is that you find out the vertical and the horizontal deflection at the point of application of this force P. Okay, so delta V and delta horizontal. So delta V for vertical, delta H for horizontal. You tell me what I should do. Any ideas?
Sir, this kind of analysis is found in proving ring experiment.
Yeah, the proving ring example, so the derivation is actually not that straightforward. I have put this as, I think, the last problem in the tutorial sheet. I mean, some people want to say that this is a very simple example. I personally do not think it's a simple example, the proving. It's one of the most sophisticated examples because a lot of the ideas are involved there. Once you see the derivation, then of course it is easy. It is just like Columbus discovering America. So after he discovered, after he went to the west and found land, everyone thought, okay, it's what's so big deal? You just have to travel west, you will find land. Okay, but you first do it yourself without looking at any book or any other derivation, then we'll see. So it's not that easy. So that's why I kept it at the last. So, but now you tell me, if you have seen those kinds of examples, you tell me how to do this.
Sir, I personally didn't see the derivation of that. I think
you think that you have not done the proving ring experiment or anything. Just based on whatever we have been discussing, you tell.
Sir, I think the similar principle works, considering the cross section and
yes, we have to take a cut section. Cut section we always have to take. Okay, so see, so let me see if I can just take this out. I've written so much things here. Okay, So what I'm going to do is take a cut section. Now cut section, suppose I take a cut section here. So I will end up with what? This kind of a thing, this kind of an arc. Now you see, if I draw the moment here, this M and this shear force, both these things are going to be equal to 0. Okay, because there is no load, there is no externally applied load on this piece. So up to this, from if you consider this theta equal to 0 at this point and theta equal to pi at this, so up to from theta equal to 0 to theta equal to pi by 2, nothing really much is going on here. But from theta equal to pi by 2 to pi, you have to include the influence of this force P. But even before we do that, let us first be absolutely clear that we are first trying to determine this delta V. Okay, so whatever we are discussing now, it is corresponding to this delta V. Okay, so I'm going to take the cut section here, and when I take the cut section here, the draw it here. It's not the best of diagrams, but I actually draw these things much better on the blackboard. On this one, I have practically very poor control. Okay, so we have this force. This is a very bad diagram actually. Just bear with me. So I have this moment M here and this shear force V. Also this entire angle is theta. So now you tell me what is the expression of this moment M, because that is our first job in terms of this P. I want to do the moment balance about an axis which is passing through this end. This end, okay? This end where the cut section has been taken. Tell me the expression. So what will be the contribution from this force P?
Some minus P or cos theta.
Okay, so let's do this properly, okay? And this picture is actually bugging me. Sorry about that. Okay, somewhat better. So what is the moment arm for this force P about this thing, about an axis which is passing through this? The moment arm will be this much. This is the moment arm. Okay. This is the line of action of the force P. This is the moment arm. And what is the value of this, or what is the length of this moment arm? So you understand that this thing is R, okay? This radius here is R. Actually, this radius, you know that this is actually passing through the mid line of this. Okay, it is not up to just this point. Okay, so if you zoom into that, the radius is actually up to this. Okay, the middle one. So in terms of this R, this length is what?
R sine theta minus 90.
R sine theta minus 90. Okay, because this angle here, that is theta minus 90. This angle theta minus 90. So this one will be actually r sine of that, that is theta minus 90. This is times the p. This is plus or minus?
So minus.
So this is clockwise, and this contribution of p about an axis passing through this one will be minus. So this is the thing. Okay, but you have to understand that this is true only for theta between pi by 2 and pi. You must be very clear about this. Okay, now that we have this thing, we can find out the
minus m minus p or sine.
Sorry?
So it will be minus m minus p or sine theta minus 90.
Oh, so this is actually plus PR, because this is clockwise and this also is clockwise. You are right. So this is like this. Good. Now we want to find out the vertical deflection. So we keep on writing this as 0 to L for the straight beams. Now what do I have to do? Tell me. It's still the length of the beam, but the length of the beam now has to be represented in terms of the theta. So as theta goes from 0 to pi, the entire length of the beam will be covered. So let me first write down this m by ei thing, the integrand, and then I will write the integration with the proper limits. So what is the, with respect to here, earlier it was dx, now what will it be?
Sir, r dt.
So dx is the elemental line segment that we are considering. Here the elemental line segment will be in an elemental arc. Okay, so this arc is the r dx. Oh, sorry, r d theta. It will be the r d theta. Okay, so this is like the ds. ds is equal to r d theta, like that. And correspondingly, this angle theta, it will go from 0 to pi. But in reality, what we have to do is we have to subdivide this thing from 0 to pi by 2 plus pi by 2 to pi. Because you see, when you are doing this thing, this is just contributing a 0. This 0 to pi by 2, because m is a 0. Okay, so this r d theta, with respect to r d theta, this is a 0. And this one, now you just go back to the previous thing and just substitute from here. Okay, this is minus PR sine theta minus pi by 2.
Hello, sir.
Yes, tell me.
Sir, I have a doubt in that moment equation.
Just a second, let me complete this. So this del m by del p, it should be minus r sine theta minus pi by 2. Yeah, let's go back. Yeah, tell me.
So like when we apply this formula, usually we take the modulus of the distance, right? But here we have taken the algebraic.
Please say that again, I could not hear you.
So the value of the distance is r cos theta, right? Not minus r cos theta.
So
But
you
here cos theta will be negative.
no, see, theta here, theta here itself is greater than pi by 2. Okay. So theta will be something like 110 degrees. Okay, so it will be like a pi by 2 plus a little bit of an acute angle minus pi by 2. So what you will have in your hand is, I mean, it's fine. Okay, nothing has gone wrong. Okay, you'll still get a positive value for the length. Is it fine?
Yes.
Huh? Tell me, be confident about it.
Yes, I am confident.
Ah, okay. So, alright, so I'm not going to do the algebra here, okay? You do it yourself. The next thing is more interesting, the horizontal deflection. Okay, you tell me now, what should I do for the horizontal deflection? Same point, at this point where the P is applied, but instead of the vertical deflection, I want to find out the horizontal deflection. What should I do? So earlier, when we did not have a force at a point where we wanted the deflection, we artificially introduced a force there, and then we proceeded by the dummy force method or the fictitious force method. Here we do have a force at the point where we are interested in finding out the horizontal deflection, but the unfortunate thing is that this applied force is in the vertical direction. We do not have a force in the horizontal direction. So since we do not have a force in the horizontal direction, we have to artificially introduce a force in the horizontal direction. Proceed as usual, and then finally we have to set that artificially introduced force equal to 0. So it is very important to note that at a certain point, even if you have a force, do not blindly go forward and just do a del P of that thing. You have to also note that not just the location is important, but the direction is also important. Okay, so for the horizontal deflection, I'm going to repeat this diagram. But now I'm going to introduce a fictitious force at this point. Let this be Q. And the plan is that ultimately I will set Q equal to 0. So just as before, if I take this cut section at theta lying between 0 and pi by 2, this piece, if I take out, the free body diagram of that will just give me m equal to 0. So I don't have to worry about that. I will take this cut section and consider again this one. So again I will copy paste from the previous one. But now I have to consider this fictitious force contribution also. Now you tell me the expression for m, this one. Let me write below. Tell me. First of all, whatever was happening for P, that I will have to include. Okay, just because I am interested in finding out the horizontal deflection whose conjugate is this Q, it does not mean that I can forget about the P. Okay, so I must include the contribution for the P also. The situation is exactly like before. Okay, I mean, because of the curvature and everything, things are looking a little bit different, but in terms of the spirit of what I am doing, it is exactly following the steps which I followed for this earlier problem. Let me show you. Not this one, this one. You see, when we were taking the moment after applying the fictitious force P here, we were still considering the contribution from the original load, the W. Because if we don't do that, you see, ultimately everything will become 0 because we are going to set P equal to 0. So definitely have to include the actual load. It makes sense also. Okay, so tell me the contribution from P. It is exactly like before. So this is P into R sine theta minus pi by 2. That was the expression, right? Yeah. Next, contribution from Q. First of all, you tell me what is the moment arm when we are taking the contribution from these forces about and towards the moment for considering an axis which is passing through this end. So,
sir, R into 1 minus cos theta minus pi by 2.
Okay, so let me first write down the moment arm. So this is the distance we are considering now. Okay, so this vertical distance, because that vertical distance, so that is the distance from this end for this force Q. Okay, so R into so what we are trying to do here is that this entire length is R, and from that I am going to remove this distance which is dashed like this, okay, which is in this dashed fashion. I am going to remove this distance. So R minus R cos of, so this angle, okay, so this much. So this much, just like before, it is theta minus pi by 2. Okay, so this entire thing is the moment arm. This is multiplied with Q. This is the moment. This is in the clockwise sense or the anti-clockwise sense?
Sir, clockwise.
So again a plus.
Clockwise.
Yeah, clockwise. So this entire thing is equal to 0. So note once again, M, the internal moment at the cut section, drawn like this, it is clockwise. Contribution from P towards a moment calculated about an axis which passes through this end is clockwise. Contribution to the moment from this fictitious force Q about an axis passing through this end is also clockwise. So all of them have these positive senses in front of them. This thing is equal to 0, and again, just like before, it is extremely important to note that this theta is lying between pi by 2 and pi. Okay, and now we just have to do like before. I will take this thing just for reference in the next page. Oh, it did not get copied properly. So now for delta H, I have to understand that my Q has to be set equal to 0, and then this integration will be again from 0 to pi m by EI del m by del Q this time, okay, and this will be RD theta, and this entire thing has to be evaluated at Q equal to 0. But just like before, this is piecewise integration from 0 to pi by 2. Contribution to the first integration will be 0 because the moment there is 0, and then we have this thing. So this m, I'm not going to replace this entire thing, okay, it's a huge expression, you just put it, the m by EI. Del m by del Q will be what? It will be simply minus R 1 minus cos theta minus pi by 2. All right. So any confusion here? Tell me.
Sir, it should. No problem, sir.
That theta business.
No, sir, it's clear. I
Okay.
forgot why this minus R came.
Okay. So I skipped one step here. Okay. So this m is equal to minus PR sine theta minus pi by 2 minus q r into 1 minus cos. Okay. So because that m is equal to basically this minus of that and then minus of that, when I do a del m del q, I get this minus r, this entire thing. Okay. That is why this minus is coming. All right. So if we are kind of okay with this, let us move on to another kind of problem. So this is again going back to the idea of combined loading. You see, when we were doing those combined loading, what just happened? Some crazy thing. Okay, so when we were doing that the combined loading, we considered the contributions from various kinds of loadings. Okay, so moment combined with axial force combined with torsion and everything. Now we will do a similar sort of thing based on the idea that earlier we have already seen expressions of the strain energy associated with various kinds of loading. Up to this point, we have been considering examples where exclusively we were considering this bending moment, okay, or the energy or the strain energy associated with the bending moment. So integration 0 to L m square by twice EI dx, and subsequently the differentiation of that. So just to refresh your memory, let me see if I have the expressions earlier written down. You have to go back a little bit before. So see, associated with torsion, I had this expression, integration 0 to L t square by twice gj tz, so all along the shaft. Then for shear, I had this expression 0 to L f v square by twice j dx, where this factor f was appearing I mean in such a fashion that it took care of the nature of the cross section. This was for shear. Then for this bending moment, by this time you are very familiar with this, and this also you are somewhat familiar, the axial load, the strain energy associated with this n square by twice AE dx. Okay, so let us go back to our example problems and consider such an example where these kinds of combined loading will have to be considered, or contributions from the various kinds of strain energy have to be considered. So we'll consider a rod, but this rod is in a bent shape. It is attached or clamped to a wall like this. This is the wall. This is A, this is B, this is C, and the externally applied load is an innocent looking simple force like this. Very, very innocent looking thing. But this alone can do a lot of things. Before launching into a discussion of the application of the Castigliano's theorem, you tell me, just from the mechanics of the problem, what are the things that are happening here? No equation, nothing, okay? Just tell me what are the things that are happening to this structure, this bent rod, due to the application of this P. What kind of possible axial forces are there, or what are the possible bending things happening? What are the possible torque-like things happening? Tell me.
So torsion at P is happening due to the force P.
Okay. So because of the application of this force P, there is a torsion which is being, or this segment BC of the rod, that is being subjected to some kind of torsion, because there is a twisting action associated with this force P, because you see there is a torque arm here. This is the length. Okay. So these are the kind of things, these kinds of bent rod, you will actually see in little pieces of household equipments, where you just have to tighten a screw or something in a toy or something. You'll find these kinds of things. What else? I'm waiting for your answers, so please tell me.
Bending moment.
Bending moment, you have to be specific. Where bending moment is appearing?
The AB.
In AB.
AB, of course it is. Then what else? In BC, in BC, bending moment is appearing or not?
Yes, sir.
Yes, sir.
Okay. So you must have some sense, okay, even before tackling any problem or writing any equation, any moment equation, or application of any particular method, whether it is deflections from the deflection of beams chapter or from the energy methods. Immediately on seeing a situation, your mind should go to the internal mechanics of the thing. Okay, so that is the difference between you and a lay person. Okay, and the more you you get into the habit of these kinds of things, no, it's like a muscle. Okay, so the people who go to gym and build muscles, it doesn't happen overnight. Okay, so it takes, I mean, months and months and probably years before that kind of body develops. Similarly, it is for these kinds of things. Like, you're training to be part of an engineer, and I'm sorry, I have this habit of lecturing. It's like more and more I get gray hair on my head, more and more I get this tendency. So this muscle is also developing from me, lecturing endlessly to students. So let me just tell you, okay, that this habit of looking into the internal mechanics of things, it's a very, very precious thing that you must develop. Okay, you see, the thermofluid science guys may have already learned this. So there are various kinds of irreversibilities associated in thermodynamics. In thermodynamics, and one of the very important irreversibilities that you study and that you deal with is the irreversibility associated with the lost opportunity to do work. I repeat, the irreversibility associated with the lost opportunity to do work. What I mean by that is that in a piston cylinder kind of arrangement, if there is a free expansion without any resistance, that's a lost opportunity to do work, and that kind of free sudden expansion leads to an irreversibility. Irreversibility is literally irreversibility. You cannot get back that work done opportunity. Similarly, in life and in your career, when you are young, at this stage, second year, third year level, there are lots of opportunities for you to develop this kind of thinking ability. Okay, once this age is gone, no, you may still be able to do quite a few problems, you may still be able to do a job, but there will be a difference between you and another student who may have day in and day out developed this ability to think on encountering a problem. Okay, it makes a huge difference. Okay, it's like this, your mental graph trajectory is like this. at this young age, so this is time, okay, and this is your mental muscle. So M here, not moment, muscle. So so at this young age, so this is like the second year level, there is not much difference between two students who one who thinks deeply and the another who doesn't think deeply. There is not much difference. It may also be possible that students who are not thinking that deeply, somehow they quickly solve problems, and then maybe even they are getting more marks in the examinations. That is also possible. But as time goes on, you see this kind of, these two graphs, no, this muscle or brain muscle, it kind of diverges, and the more time goes, this gap becomes more and more. So a person who has developed, a student who has developed this ability to think on encountering these problems deeply, his brain ability after 3-4 years will be at a much advanced stage compared to a student who has just solved problems like at face value without thinking deeply. Okay, I'm done lecturing. Let me solve the problem. So what do I do here? So as before, I will take a cut section, but now I have to take the cut section respecting the three-dimensional nature of it. I will also consider this AB and the BC segments separately. Please also note that this distance is L1, the AB is L1, BC is L2. Okay, so first I will take a cut section somewhere within this AB, like this. Okay, and I'll separate that out. This is P. Now my moment. You see, I'm trying to draw this in a three-dimensional kind of thing. Okay, so this is V and this is M. I should have drawn this in green color, but anyway, you tell me the expression for M. Oh, by the way, this distance now, I don't want to write X and Y. Rather, I will I'll represent it through some generic S1. Okay, now you tell me the expression for M quickly.
So M minus PS1.
M minus PS1 is equal to 0. So M is equal to PS1. So this is for the part AB. Okay, and just to make things absolutely clear, you write S1 is lying between 0 and L1. Right? This is easy. Next part is BC. Here you have to be a little bit careful. So we will separate out the BC. So what we are going to do is we are going to take a cut section here. Okay, so somewhere here. But at the same time, I'm going to remove this AB part also. Now removing the AB part means what? I'm effectively doing this. This is the entire AB part, okay? And this is from B to a generic distance. So this is the entire AB thing. The force was applied here. At this point, I have some kind of a shear force here, some kind of a moment here. But what I'm really interested here is to see the kind of things that remain here after this AB part has been removed. One thing is very clear, that this force P has to appear here. Like this. What else must appear here? Tell me. This is the crucial part.
So the moment PL1.
Moment PL1. Now this moment PL1, you tell me it is suppose I say that this is X and this is Y and this is Z. That moment PL1 you are talking about, that is directed along which axis?
Along X.
Along X axis. Very good. Axis. So along X axis, fine. So along positive X axis or along negative X axis?
So negative.
Sir, positive.
तो नेगेटिव में आ बोला तो पॉजिटिव ही बोलोगे, एक्सप्लेन करो.
Sir, actually it is from seeing from right side it is clockwise. So
Of course, right side, yeah.
Yes.
So it is like this. Okay, so this is PL1. There should not be any doubt about it. Okay, there is no convention, nothing. This is real PL1 like this. Okay.
Sir, excuse me, sir.
Yes.
Sir, we could have solved this case without separating AB. We will also get the same thing.
Yes, you will get it.
So why are we preferring this way? I mean, is there any advantage?
No advantage. I'm just torturing you.
Okay, sir.
No, you will get some clarity in this kind of thing, okay? Because you see, this is a relatively simpler thing. I mean, you just have one bend. You will also have problems where there are multiple bends. Okay, so that's why, I mean, I feel it is kind of easier to do these kinds of things. And somehow it's in my head that if you do these kinds of things, then in order to code it up, it is somewhat easier if you have this clarity in your brain. Anyway, we are not done with this piece, okay? So next is that I want to say that this length is S2, where this S2 is lying between 0 and L2. You tell me what else must be done to complete this picture. Is there any other moment or anything being applied at this end, B?
No, sir.
No. Good. At this end now. So at this end, I am going to draw one moment. Okay. Of course, one thing is correct, that there will be a counterpart moment associated with this torque PL1. Looking from the right hand side, this is like this. Okay, this is the sense. You please try to follow my this icon, this cursor, like this. Okay, so correspondingly you are going to end up with a moment on this direction like this. But in addition to that, okay, I'll draw that a little bit later, there will be a moment, a bending moment. Now that bending moment, I'm going to draw a curved arrow. You tell me on which plane, referring to this XYZ axis, should I draw that curved arrow?
XZ plane.
Very good, XZ plane. And so it's like this. This is the moment. And by the way, that should be in green color. All right. There should be one shear force also. So I will just draw the shear force like this. I will draw the shear force here like this, because I want to respect the convention that when I draw a cut piece like this, I draw the moment like this and I draw the shear force like this. So if you see, that's why I'm drawing it like this. But this V is actually going to be equal to minus of P if you write down the expression. And finally, I'm going to draw the torque, which is like this. This torque will have the magnitude equal to PL1. So now this diagram is kind of complete. And now I want to I want to write down the total strain energy expression. Okay, usually I have not done these kinds of things, the total strain energy, but this is a new kind of situation, so I'm just trying to make everything nice and explicit. Total strain energy. So first of all, due to bending. But bending where? Let us not forget that we have also done the AB part. First of all, we'll write for that. So 0 to L1 m square by twice EI ds1 plus, coming to the BC part, integration 0 to L by 2 m square by twice EI ds2 plus, tell me the contribution from the torque.
That's 0 to L by 2 T square by 2 GJ. Integration inside.
Very good. Okay. Now, actually, there is another contribution, which is the one associated with shear. In fact, in all the previous problems, there will be contributions from the shear also. Okay. But usually, we do not take that contribution. I have put one problem in the tutorial sheet. Okay, so I'll show you the tutorial sheet problem. This is the tutorial sheet. Most of these problems are quite straightforward actually. Some of them may be slightly bit lengthy, but I mean, they are all straightforward. You see this question number 5. Here I have asked you to determine the deflection of the beam caused only by bending and caused by bending and shear. So this is the answer that you get considering only the bending, and this is the part that you get considering both bending and shear. Okay, and you will realize that the contribution from the shear is actually very small. Okay, very small compared to the bending. That's why usually we neglect it. Okay, now coming back to this thing, just to complete this thing. So this is for the part BC and this is for the part AB. Now we can quickly go ahead and, oh, I did not state the question. So we are interested in finding out the deflection at the point A. Okay, so you find out the deflection at the point A along the direction of P. So no complication there. So now I'll just quickly find out the deflection at A. That is just del U del P, and let me just quickly write down the corresponding integrations. So this is m by EI del M del P ds1 plus integration 0 to L by L2, again m by EI d del M del P ds2, and I'm not writing the intermediate steps for this, even though I have not done it before. So the del P of this can similarly be done. It is going to be twice 2 by twice GJ. The 2 will cancel and then we'll have del T del P. Okay, and I have the answer for you, so you can check later on. This first integration is going to give us PL1 cube by 3EI, which is to be expected. The second one similarly will give us PL2 cube by 3EI, that also is to be expected. And the last one will give us PL1 square L2 divided by GJ. Okay, so that's it. So another argument in favor of energy methods. Okay, so if you can somehow manage to find out the proper internal moments and torques, then determining the deflections becomes rather straightforward compared to the methods which you have learned in earlier chapters. This is certainly good. But do remember that we are repeatedly using the Castigliano's theorem and being very happy with ourselves. That's, look, we have learned this extremely useful method, and we are doing this. But there is a very great temptation of applying Castigliano's theorem in those problems where it is not actually applicable. Like the problem situation is such that it violates the requirements or the basic assumptions which are behind Castigliano's theorem itself. The most basic thing is that the material behavior must be linear elastic. It is a good fortune for us that most of the common engineering structures or structural materials, they do follow the generalized Hooke's law. But this situation is not going to be so by the time you become professional engineers, because this paradigm of traditional engineering materials, it is very quickly breaking down. It is certainly going to be true that buildings are still going to use a lot of steel, bridges are still going to a lot of steel, but engineering is not just limited to bridges and buildings. Okay, there are many other things that engineers fabricate, and many of those like proper 21st century products will involve materials which are non-metallic, which may be based on various kinds of polymers. I'm not just talking about children's toys, okay? Various kinds of futuristic prosthetics which are being fabricated for helping out people with amputations in their hand, like somebody's hand has gotten cut off or some problem is there in the body. To support their body, some kind of like ultra modern structures are being made to help them. So those are not made from steel or these kinds of hard things, okay? They are made from various kinds of polymeric materials, and there the stress strain relationship is not linear. Okay, the effect of temperature also is there significant. So in those kinds of situations, do not go about using Castigliano's theorem blindly. Okay, of course, if you fall back on the proper use of the virtual work principle, then you are never going to get cheated. Virtual work principle is a general method. It will always be applicable. All right. So with this, I'll stop my lecturing. You please go to your next class and we will meet tomorrow. Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.
Yeah. Bye.
Thank you, sir.
Bye.
Thank you, sir.
Thank you.